Welcome back. So in the last few lectures, I've been showing you how to numerically compute the derivative of a function f of x or f of t. And in this video, I'm going to show you how to do the opposite, how to do numerical integration, so to find the area under the curve of a function. And this can be a little confusing, this terminology, because numerical integration actually means two different things. There is numerically integrating an ordinary differential equation to find a trajectory through phase space. That's one interpretation that I'll talk about soon, probably in the next lecture. But this lecture, when I say numerical integration, I literally mean numerically computing the definite integral, which is the area under a function from point A to point B. Okay, so we're going to find the area under this function using kind of numerical methods. Good. And just like before, we're going to take kind of the Riemann integral definition that you would take the limit as delta x goes to 0, where these little rectangles become infinitesimal. That's the Riemann integral. And we're not going to take that limit, and we're going to see what happens for a finite width area approximation. So just some notation, we're going to assume that our data is defined at points x0, x1, x2, x3. In this case, all the way up to, let's say, xn, x big N. I'm going to similarly define my data points. Maybe I'll make these pink. F0, F1, F2, F3, Fn, where specifically I'm defining that, whatever Fk for whatever k value here, Fk is just f evaluated at xk. Fk, this data point that I'm using the subscript k, that just means fk equals my function evaluated at this point xk. So f0 equals f of x naught, f1 is f evaluated at x1, and so on and so forth. Good. And I'm also finally going to assume that this left point is a point, I'm going to call it kind of like A, that's the left bound of my integration. My right point is some point B, that's the right point of my integration. And I clearly have n of these little steps between A and B, because this is big N, there's n of these little steps, and I'm going to assume for now that these are spaced at a constant delta x. You don't have to assume that, but that's going to make our lives easier for now, is to assume that these are evenly spaced. We'll relax that in a minute. So maybe I'll change to orange. So n is the number of whatever, like rectangles or data points, of number of points. And so delta x is b minus a divided by big N. That's kind of the width between each of these data points. Okay, that's my delta x. And so the absolute simplest thing we could do is, remember the Riemann integral basically chops this up into rectangles that are either kind of at height f0, f1, f2 times width delta x. It chops this into a bunch of rectangles and then takes the limit as that rectangle width goes to 0. That's how the Riemann integral is defined. And so I think I'll just actually write this out. So the normal way to do this integral from a to b of f of x dx is equal to, typically we say it's the limit as either delta x goes to 0 or as n, the number of divisions, goes to infinity. I'll just say limit is n goes to infinity. Doesn't matter, also the same as delta x going to 0. They're the same thing. Of the sum from k equals 1 to n of the width, the height of these rectangles times the width of these rectangles. So I'm literally just going to, how do I want to draw this? I guess what you would do is you could, my formula that I'm going to use, that I'm going to derive, is for the right-handed rectangle rule, and there's many ways of doing this. So what I'm going to do is I'm going to say that this is approximately equal to the area of this rectangle here, plus the area of this rectangle here, plus the area of this rectangle, this rectangle, this rectangle, and so on and so forth. So we're literally going to break this up into a bunch of rectangles, and we're going to compute the area of all of these rectangles, and we're going to add these up, and that's going to be our Riemann integral. And then we're going to take the limit as delta x goes to 0, or if you like, as I have infinitely many points between a and b. Okay? And so essentially what we're looking at is at a given k, at k equals 1, 2, 3, 4, so the first rectangle is k1, the second rectangle is k2, and so on and so forth. So I'm going to take the height is going to be f of a plus k delta x. So if k is 1, then it's a plus k delta x is my x1 point, so that's f of that point. That's this height of this rectangle here, times delta x. Okay, this is literally the Riemann integral approximation of the area under this this blue curve from point A to point B. So I'm taking the height of f evaluated at x equals a plus k delta x. So for k1, for the first k, that's at height f of x1, that's my first height of my first rectangle. At k2, it would be a plus 2 delta x is f of x2, which is the second rectangle height, and so on and so forth. So I add up all of those rectangles, and the area of each rectangle is its height here times its width here. And you would normally take the limit as n goes to infinity and delta x goes to 0, and this will be the exact integral. So if instead of taking this limit as n goes to infinity, what if I didn't? What if I just drop this and I take this finite sum for finite delta x? So that's what we're going to be talking about today. How does the error scale with that? What are the properties? Does it work? Does it not work? Things like that. And I'll take one more step to simplify. A plus k delta x is just the height of my rectangle at that point. So this equals limit as n goes to infinity, sum of k equals 1 to n, f of, let's say, x k delta x. And this is the right-handed or right-sided, I don't know exactly what everyone calls it these days, but basically you have this little rectangular interval with these 2 points, and you could use the value at the right-hand side, this x1, or you could use the value at the left-hand side, this little x0. So this is what I'm going to call the right-sided Riemann integral, or the right-sided rectangle rule, approximation of the integral. Now, if I'm actually taking an honest-to-goodness limit here, technically this will also equal the limit as n goes to infinity, the sum of k equals 0 to n minus 1 of f of xk delta x, where now all I've changed is the limits of my summation. And so now instead of making the height of my rectangle based on the right data point x1, I'm making it based on the left data point x0. So I'm not really sure I can draw this very cleanly, but the left-handed integral rule would be using this area of the left side of the integral. And so they're slightly different. So one of them is going to overpredict on positive slopes and underpredict on negative slopes. The other one is going to do the opposite. Okay, and this is called the left-sided rectangle. Good, and I'll just maybe draw a teeny little picture here. So like literally if I have this little piece of the curve here, the left-sided integral is going to use the left point to approximate the area, okay, like this. And the right-sided rectangle rule, same exact curve. The right-handed rectangle rule is going to use the value at the rightmost point to approximate the area. Okay, maybe I'll draw it like this. And so like I said, if I have a positive slope of my function, the left-sided rectangle is going to underpredict. It's going to miss all of this region here, so this is missing. And the right-sided rule, the right-sided rule is going to overpredict. It's going to actually overestimate all of this stuff here. So you can already see where the error is going to come from. It's going to come from the first derivative of f. Okay, good. That's actually it for now. That's actually what I wanted to show you. What I'm going to claim is that now you can actually take this expression and you can work out what the error in the approximation is if I don't take the limit as delta x goes to 0. So how do I want to say this? So these are kind of like, remember when we did the finite difference derivatives, we did the forward difference and the backward difference? These are kind of like the forward difference and the backwards difference, but for numerical integration. And like in differentiation, those had the most error and the worst scaling. These also have the most error and the worst scaling. So clearly you can kind of already start to see that there is a better alternative, that instead of using the left point or the right point, why don't I use both points? So an even better approach would be, let's say I have these 2 points here. Why don't I actually take the area to be this little trapezoid here? So I now have this area of this trapezoid. So this is going to be called the trapezoid rule. So there's the right rectangle, the left rectangle, and then the trapezoid rule, which I'll write out here. So the trapezoidal integration. And this is actually pretty easy. It's literally just the average of left-handed and right-handed. So it's literally equals 1/2 right-sided plus left-sided integrals. Okay, pretty easy. And you could numerically compute that by, instead of just taking the area using the left point or the right point, you basically average those points and use the area based on that average value. That's equivalent to the trapezoidal integration, is to average those values. Okay. Good. And so this is actually going to have even better error. This is kind of like the central difference. So this is kind of like backwards difference, forward difference, central difference, but for integration. Okay, so we're using more information here and getting a better approximation. And in MATLAB and Python, this is literally like the trap_z command. So this is the trap_z command for a trapezoidal. If I had data x and data f, I would literally type in x comma f, and it would compute this. And notice that none of these actually have to have a constant fixed delta x. Like all of these would be totally valid for the x, some of these x to be fat and some of these x to be skinny. It would be totally fine if I sampled my function so that maybe I sample it really wide and then fine and then wide, like this. That's totally fine. I can still approximate the the area using these little rectangles or trapezoids between these points. So if I liked, I could still build a trapezoid, between these points and this point, and I can do kind of the trapezoidal integration and approximate the area, even if I have some points more finely represented than others. That's totally fine. So the delta x spacing doesn't have to be uniform for any of these algorithms. It's pretty easy for it not to be. And you'll notice actually that the trapezoidal integration is going to be exact, except for there being this second derivative curvature here. So the trapezoidal rule, just like these guys overshot or undershot the value depending on the slope, the trapezoidal integration error is coming from the second derivative, from the curvature. So regions that are approximately linear are almost perfect, and you only miss this part here because of the curvature. This is the error due to curvature. And remember, curvature of a function is f double prime. Okay, the f double prime, when f double prime is large, the trapezoidal integration is not going to do well. So it's not going to do well if I, if I zoom in, if I have something that looks like that has a lot of curvature, my trapezoidal integration is going to miss. This is all kind of error here. This is all missing. Missing from trap z. Okay. Now, we can compute the error of each of these schemes using kind of the same basic idea that we did for finite derivatives. We would basically write out a Taylor series. We would appropriately plug them into the right places of these different terms. And we would basically find, so I might do a lecture on that, I might not. I actually have some old lectures from when I taught this about 10 years ago, so I might put a link to that because I think that's actually a pretty concise version of how to actually compute all of the error of these numerical integrations. I'm not super duper concerned with like deriving all the Taylor series error for these. It's probably like a homework assignment for you all. But the upshot is that if I remember correctly, left-sided and right-sided, for every little rectangle, they have an error that is proportional to delta x squared. So let me just write that out. So these each have what I'm going to call a local error of proportional to delta x squared, meaning for every single little box, they have an error of delta x squared. And again, this comes from the Taylor series, like the Taylor series approximation, local error of delta x squared. But because I'm adding up approximately, 1 over n, I'm adding this up n times, and n scales like 1 over delta x. This accumulates a bunch of times. I'm adding up a bunch of these delta x squareds, and I'm adding up 1 over delta x of them. So kind of the global or total integration error over this entire area scales like delta x, which is actually pretty bad. That's not a good error. Okay, so that means again, if I want my error to be 10 times smaller, I have to decrease my delta x by a factor of 10. Okay, so this is again just like forward difference and backwards difference for derivatives. The total error scales linearly with delta x, with the increment. Okay, the trapezoidal integration, if I remember correctly, and I could be wrong, so double check this. You can Google, trapezoidal integration error scaling, but I'm pretty sure that this is local error of delta x cubed, which I think means we have a total error of delta x squared. And my intuition, the reason I feel like this is because, again, the error here was proportional to a first derivative, the slope of f. If the slope was positive, it behaved one way. If the slope was negative, it behaved another way. Whereas the trapezoidal integration rule is a function of the curvature. And so if I did a Taylor series expansion, the first derivative and the curvature, those would be 1 delta t apart in the Taylor series. And so I'm assuming this is, 1 delta x. And so I'm assuming that this has 1 delta x better error properties than these. Kind of like this is a central difference and these are forward and backward difference. Again, I think that this would hold. I'm not 100% sure, but I'm pretty sure that's true. And again, that's way, way better. That means if I want a better error by a if I decrease my delta x by a factor of 10, this actually gets 100 times better total integration error, while this only gets 10 times better. Good, what else do I want to tell you? There's a really powerful method called Simpson's rule. Simpson's rule is probably the best easy numerical integration scheme. Simpson's rule. And essentially, if you like, under the hood of Simpson's rule, this works if you have 3 data points. So if I have some, I've got 3 data points, let's say, f, I'm just going to use f0, f1, f2, and I want to find the area, the area under this thing. And of course, you can shift this to fk plus 1, fk plus 2, or fk minus 1, fk plus 1. You can center this wherever you like, but these are easier indices for me to work with. Simpson's rule says that the integral from x0 to x2, from here to here, is going to equal of f of x dx, is going to equal, okay, so it's delta x over 3 times f0 plus 4f1 plus f2. So this is some weird combination that you would get from Taylor series expansion, presumably, minus delta x to the fifth over 90 times the max fourth derivative of x in this region, okay? So this is really good, actually. So this means that locally, at every little local width rectangle here, this has delta x to the fifth local error. It's way better than either of these, which means it's local error. So this is local error delta x to the fifth, which means it has a total error of delta x to the fourth. So it blows both of these out of the water. And you'll find in the next few lectures, just like I had forward difference, backward difference, central difference for derivatives, and I've got right-sided rectangle, left-sided rectangle, trapezoidal difference for derivatives. This is basically a higher order scheme. You can essentially think of this as building a spline, a cubic spline interpolation through these points, and then analytically integrating that cubic spline. I believe that's what Simpson's rule does. And it pushes that Taylor series error way, way out to order delta x to the fifth locally. And this is actually kind of numerically going to be the analog of a fourth order Runge-Kutta scheme in numerical integration of ordinary differential equations. That's a teaser for a future lecture. Okay, so this was an overwhelming amount, but basically I presented you with 4 types of integration. Left and right rectangle rules are kind of my basic rectangular Riemann integrals. They have crappy error scaling, but sometimes that's good enough, quick and dirty. If you want to do better than that, you can do trapezoidal integration, which geometrically gets you more of this area by just averaging these two, and it also has better error scaling, kind of like the central difference had better error scaling. And if you really need a lot better error, you can do something fancy like assume that there's some cubic spline between these points, fit that, integrate it analytically, and use Simpson's rule, which is actually very simple to write down numerically, and it's got way, way, way better numerical accuracy scaling with delta x. So I think what I'm going to do now is I'm going to erase everything, and then I'm just going to code this up a little bit in Python and Matlab, and we'll just get a little feeling for how these errors scale and things like that. Yeah, and I'm telling you what these errors are based on a Taylor series, but I haven't actually shown you. I think what I would do here is I would say f of x plus delta x, or f of x minus delta x, and I'd expand those out, and I'd use the Taylor series, and I'd get something that told me what these errors were, and I do the same thing for trapezoid, and you can do the same thing for Simpson's rule. That's, that should be old hat for you right now, and if you really want to understand this, you can definitely, do that on pencil and paper as a homework example. Okay, I'm going to erase, and then we'll do some coding. All right, 1 second. Okay, so I've given myself a little room to work here, and I've erased all of the formulas because I don't think that's going to be super duper helpful. You can, intuit how to compute the left and right rectangle rule and average them for the trapezoid rule. I've left these pictures because these kind of show what we're doing. And what we're going to do now is actually just build a little function like sine of x and integrate this from 0 to 10. So the exact value is something like 1.8391, or it's approximately exact. This is very accurate. And then we're going to integrate it using these different techniques to see kind of what the error accuracy is. Okay, so we are going to define our a and b limits as 0 and 10, and we're going to start with a really fine delta x of 0.01. That's presumably going to be for plotting, so I want to plot this thing on a really, really fine domain so you can see like the crisp, clean sine wave. That's this f means fine, and so I'm going to plot. I've changed f to y here, so this is yf, not f whatever, it doesn't matter. You can call this y of x, it doesn't matter. So we're integrating y of x here. And so we're going to plot that fine function, and now I'm defining a coarse delta x of 0.5. That's actually massive. That's a really big delta x for a sine function. And this is some plotting commands to kind of show pictorially what I've drawn here, which is using the left rectangle rule, I believe. So the left point here, you use that left area to create this kind of step function, and the area under this step function is going to be our approximation to the area of the true sine wave in orange. And so again, you can see pretty clearly that the left integral rule is going to underpredict these triangles when the slope is positive. it's going to overpredict these triangles when the slope is negative. We already saw that. It's pretty clear from this. And similarly, if I use the other rectangle rule, it would do the exact opposite. It would be over-predicting positive slopes and under-predicting negative slopes. And if I average them in this trapezoid rule, it's going to do a much better job of not under-predicting or over-predicting those slopes, and it's only going to be bad when I have high curvature. Okay, so now we can actually go through and compute the left rectangle rule area, the right rectangle rule area, and the trapezoidal rule. So this is literally just a for loop that's going through all of these data points, and it's either using the y value on the left-hand side or on the right-hand side to compute that area. And then the trapezoidal rule is averaging them. It's averaging the left-hand and the right-hand area rules, okay? Okay, there's also these nice built-in Python functions. Okay, so let's just run this. These built-in Python functions, you can just use the sum of this, that's the left rectangle rule, the sum of this on the right, that's the right rectangle rule, or the trap z is the trapezoid, that's area 1, area 2, area 3. And I think that's, this one, and this one. Yeah, in this one, these are actually much closer to the values, and they're different than these. So I think something's wrong up here. I can't obviously see it off the top of my head, but there's something, I think, wrong up here. Okay, so we're going to try to estimate the area of a function using these different rules in MATLAB. And let's just go to the very top. So what we're going to do is we're going to define our sine function on an interval 0 to 10, a to b. And we're defining this fine resolution delta x, a very small delta x, basically just to plot my sine function so you can see a nice clean version. And then a really coarse big delta x of 0.5 to show kind of the sampling that we're going to use for these rules. And I think what I'm going to do is just plot to begin with. Okay, so this kind of shows the sine function in orange, and then these blue ladders. This is, I guess, the left rectangle rule. And so the sum of these left rectangles would be my left rectangle approximation. So you can see it's a pretty bad coarse representation. And I can compute my left rectangle rule by adding up all of my left points times delta x. I can compute my right rectangle rule by adding up all of my right points times delta x. And the trapezoid is just the average of those two. You can use the built-in MATLAB commands, just sum over all of the left points up until end minus 1, or sum over all of the right points from index 2 to the end. Or trap z is this really nice, built-in trapezoidal rule. You can do that as well. And you can either give it a list of x locations, xc, or you can not give it a list of x and it'll assume unit spacing, and then you have to multiply by delta x. And then finally, these area f's are the fine resolution approximations using that fine grid that we were using for plotting. So I'm just going to run all of this all at once. Okay, and area 3f, that was one of the fine ones, 1.8391. I'm just going to write that up, 1.8391. And so now we're going to compare, okay, area 1 was left rectangle, area 2 was right rectangle, and area 3 was trapezoidal rule. And so you can see that area 1 is overshooting. Area 2 is undershooting, and area 3, the trapezoid rule, is almost, it's definitely the closest to the area using a very, very small delta x. Okay, so this kind of just shows that our left and right rectangles are less accurate. Our trapezoid, even for a very coarse delta x of 0.5, is much, much closer to the true value if I used a teeny tiny delta x. Okay, so that just kind of shows how to code these up and how to assess the error. Okay, that's everything I wanted to show you with numerical integration. So that's it for today. Thank you.